Alrighty, I'm going to go ahead and get started. Welcome to Lagoon Water Chemistry, a balancing act. I am Julie Hartwig. I'm a lagoon specialist at Triplepoint Environmental. So an overview of what we're going to be talking about today. I'll start by introducing Triplepoint, who we are, why we're doing Lagoon webinars, especially if you haven't joined us for one of these before. And then I'll get into it. So the focus of our water chemistry webinar today is going to be largely on pH. So we'll start off with what is pH and what determines the pH in a lagoon. Then we'll move into alkalinity, which is related to pH, but not exactly the same thing. Alkalinity is very critical for nitrification, the process of ammonia removal. So we'll go over that connection, why it matters, and how to calculate what you need. And lastly, we'll go over some methods of controlling pH in the lagoon and adding alkalinity if necessary. So just an overview of who Triplepoint is. We are a lagoon services company. Lagoons are all we do, and that's wrapped up in our first kind of motto here on the left. Lagoons do it better. We believe at Triplepoint that lagoons are a technology that is going to remain important in modern days with modern permit limits, that they're very cost effective for things like industrial plants in small towns, and that lagoons can be upgraded to meet any wastewater treatment standard that comes out. Our second unique is we've got a tailored process. We treat every lagoon system that we talk to as a blank slate. We want to work with you, whether you are the owner or the engineer, to find a solution both for your problems and one that fits your budget. So it's a tailored process. We work with you rather than trying to just give something off the shelf. And lastly, we say it, we do it. We are in the business of making all of our customers happy customers. And that's why we give a we say it, we do it guarantee. We not only warranty our products, but we guarantee the process outcome for 2 to 5 years, just to show how much confidence we have in our process and our belief that you will be a happy customer once we go through our design process. So Triplepoint has been doing lagoon webinars for a couple of years. We've stepped up the frequency now that so many people are having conferences and trainings being canceled. So we're trying to do them weekly. So next up in our webinar series, next week, my colleague Brady will be presenting a webinar on ammonia removal for lagoons. We'll go over why ammonia is being regulated now, why we should care, the process of nitrification and how ammonia is removed, and then how specific that is to lagoons. What are they good at? What are they not good at? And what are the options on the market for removing ammonia in a lagoon system? And then as an additional service that we are working on providing now that training is becoming harder to get, in-person training especially due to the virus, is we've launched our online Lagoon University. So this is going to be a platform where all of our webinars are recorded and they're available on demand. And we're working on getting these registered in many different states for CEU credit. For operators, not just PDHs for engineers. If you're in a particular state and you want to make sure that we get you on the list, please let us know in the follow-up survey after this webinar, and we'll put you on the list to make sure you can get an attendance certificate and get all these webinars registered as CEUs as training hours for whatever you may need if you are a lagoon operator or an engineer. So that'll be lagoonuniversity.com. And we're already registered in several states, so the ball is rolling. And lastly, for the introduction, this is just an overview of our products, what we actually do here at Triplepoint. We focus on providing solutions to upgrade lagoons. So our first flagship product is over on the left here is our Ares Lagoon Aerator. This is a combination of fine bubble and coarse bubble diffused aeration. So what this means is we create an aerator that is fed with a blower on the shore. The great thing about that is that all the moving parts are on dry land where they don't need a boat to be accessed. And that air is then piped out to these diffuser units in the lagoon. These can be just dropped into an operating lagoon. You don't have to take it offline to install them. And they're easy to individually retrieve for maintenance over the years. Our second major product is our nitrox lagoon ammonia removal reactor. This is a 2-cell reactor that's placed after the first couple of lagoon cells to remove ammonia. We basically let the lagoon do what the lagoon is good at, which is removing BOD. And then we build this reactor for the nitrifying bacteria that have very specific needs in order to get them to function efficiently in a very small footprint. Our third product is an expansion of the nitrox reactor for nitrogen removal. So ammonia removal, you're just changing ammonia into nitrate. But then the nitrox plus D denitrification reactor takes that nitrate and removes it from the water entirely by adding an additional cell or series of cells as necessary. And lastly, we've got the PhosBox. This is a tertiary lagoon filter that can be used to filter out phosphorus with some chemical precipitation, or just as a polishing filter to reduce BOD, TSS, whatever you need to hit your permit. So now we get into the important part of lagoon water chemistry as examined through pH. So what is pH? pH is a measure of the chemical balance in the water of the lagoon. There's a lot of things going on in that water. There's a lot of contaminants, but pH is a window into how those are all balancing out together. pH specifically means power of hydrogen. That's what it stands for. Because we're measuring here the hydrogen ion, H+, in the water. I'm not going to make you do math, but I just want to explain how we get to the numbers that we do. So the pH is a measure of the exponent, the log of hydrogen, because we're talking about quantities here that are very, very tiny. So an example here, if you have a hydrogen concentration in the water of 10 to the -3, this is 0.001 concentration of hydrogen that's expressed as 10 to the -3rd. What we're looking at pH here is just this value up at the top. So 10 to the -3rd equals a pH of 3. The pH scale, the possibilities of this hydrogen exponent run from 0 to 14, with 7 being neutral, right in the middle. And it's worth noting that this scale is kind of inverse. The lower the pH you have, the more hydrogen is in the water. It's a little bit backwards. So lower pH means more hydrogen. And we'll go over that and why that matters in the future. But this is just an overview of the pH scale. 1 to 14, lower numbers are acidic, higher numbers are alkaline or basic, and then 7 is neutral. In normal lagoon conditions, the water in a lagoon is going to be fairly neutral. It's going to be somewhere between 6.8 and maybe 7.8 is the typical municipal lagoon pH range. That's a great deal because most of the bacteria that we rely on for microbiological wastewater treatment, they prefer a neutral pH. So this range of ideal BOD removal overlaps pretty nicely with typical lagoon pH. If you've got an industrial plant or if you've got some bizarre conditions, you can get pH that's lower or higher than this. But once you get outside of this range, you're going to start having issues with your biological treatment. Every type of bacteria has a preferred pH for themselves to live in, and you take them outside of them and they're either going to stop working or they're going to die. One particularly tricky, picky type of bacteria that we'll talk about more later are the bacteria that do nitrification, ammonia removal. They are very specific in what they want. They want a pH ideally in the upper 7s to low 8 range to do their best work. And then if you go get a pH much below 6.8, they actually start to die. So that's your normal pH range, but then what are some conditions that give you unusual pHs? What does that mean? We'll talk about this more later, but this is just a good summary to put all this stuff in context when we talk about pH levels. If you've got a low pH, that's probably because you have organic overloading. Low DO bacteria produce acids under those conditions where they're not aerobic and they're working maybe overtime, harder than they should be. That can start to drop your pH range below the normal. On the opposite side, we have a higher or rising pH. A lot of times, it is due to algae overgrowth. Algae have a very strong effect on pH, which we'll go over in detail. And they can send your pH of the water way above 10 in the worst conditions. And then on both sides of this, if you've got industrial influent, that can have high acid influent or high alkalinity influent. Industrial systems are a bit of a wild card when it comes to pH. So how do we get here? Why do we have this hydrogen ion in the water, and why do we care? At the basic level, how this starts off is that water, H2O, we all know it, we're familiar with it. It has the ability to split itself up into electrically charged ions of hydrogen is H+, and hydroxide is OH-. And usually we talk about H+. I write H+ here because it's shorter and easier to write, but H+ usually does not exist in that form in the water. What it likes to do is stick itself to a second water molecule and create H3O+. That's what we've got a description, a visual of at the bottom here, is that you still have a positively charged and a negatively charged ion, H3O+ and OH-. The H3O+ ion is called hydronium, but I'm going to basically just refer to it as H+ hydrogen for ease in this presentation. So when you've got water splitting up like this, there's a chemical law that the powers of H+ and OH- always add up to 14. That's every chemical has a way that it balances, the way that it splits according to different pH and different chemical balances, and water, the magic number is 14, which you'll notice is the pH scale, runs from 0 to 14. And it's for exactly this reason. If you've got 100% H+, you'll have a level of 0 because it's pure H+, it's very big, versus if you have a huge amount of OH-, if it gets to 14, sorry, I got that backwards. If H+, you've got a huge amount of OH-, this is 0, then H+ will be 14. It'll be extremely, extremely tiny, 14 zeros, and that water will be extremely alkaline, extremely basic. So if you're doing water chemistry, you can use one of these factors to determine the other. So say I gave you a number from a lab or a homework problem that we know OH- has the power of 10 to the -9. 14 minus 9 is 5. So that means you can determine that H+ is 10 to the -5, or that water has a pH of 5. This is the most basic level of water chemistry. Pure H2O, in the absence of anything else, will actually have 7 of each. They'll be equal. H+ and OH- will both be 7, which is why a pH of 7 is neutral. That's the natural state of water according to this natural law. But in real life, we don't usually have just pure water. We have stuff in our water. And substances that dissolve in water often form charged ions, which are just molecules and atoms floating around in the water with a positive or a negative charge. So an example here, we have sodium chloride, which is normal table salt, NaCl. You add that to water and it splits up. You have a sodium ion, Na+, and a chloride ion, Cl-. we refer to these ions, if they're positively charged, as cations, and negatively charged ions as anions. And another natural law is that nature always seeks a balance. Water wants to be electrically neutral. If it's not electrically neutral, you've got a battery or an electric current going on, but we don't have that in a lagoon. So the water has to balance itself. It wants the anions to be equal to the cations. So what you end up with then, if you were looking at the total sum of the water, is this big equation of all of the chemicals that are in the water. You have all the positive ions on one side. For example, I've used some common ions here of calcium and magnesium. These are commonly found in source water as water hardness. And then you've got the H+ from the water itself. And then on the other side, you have the OH- from the water itself. And then you have your various anions that are commonly in the water. This is bicarbonate and this is carbonate. We'll talk about these guys later, but they're also commonly found in source water, coming from limestone rock or the air itself. And then chloride at the end, also just a very common natural water. This is very simple. This is an extremely oversimplified water situation. If you looked at the influent into Lagoon, you'd have probably hundreds of these ion types on both sides of the equation. If you consider everything that's going into the water, every cleaning product in every household, everything that people are eating and passing in their waste. And nobody has time to determine what all is exactly in the water, how much, how does it balance, which is why pH is so important. The water balances itself out by changing pH. If you go adding a whole bunch of pure calcium, for example, it's going to throw this out of balance. How does the water compensate for that? Well, since the calcium is on this side, the OH- on this side is going to go up to balance it out, which means this is going to have to go down so that these guys still add up to 14. So that's a complex process that I don't have time to get into in this webinar. But really what it adds up to is pH is so useful because if we just look just at this hydrogen ion, it gives us a window into this entire chemical balance without needing a lab and all these tests. We can measure this simple thing and it gives us a lot of clues about what else is going on in the water. That's just because it is a measure of how the water is balancing itself out. So of all of the water species that are in the water, some species have more of an effect. The ions in the water have more of effect on pH than others. And we call these acids and bases. Acids are substances that reduce the pH. They make it more negative. Often they do this by straight up adding new H+ ions into the water. But there's other mechanisms as well, such as if they delete OH- ions, it has the net effect of increasing H+ ions. Bases are the opposite. Bases are substances that raise pH. They can add OH- or other negatively charged species, but they raise the pH. They deplete the amount of H+ in the water. So these are things that really tilt the balance between the two water types, H and OH. So here's an example on the bottom of how this max works out a little bit. We've got hydrochloric acid is HCl. When that dissolves in water, it breaks up into H+ and Cl-. You'll notice, unlike NaCl from our previous slide, Cl- is the same, but it's pretty neutral. It's just sitting over here being negative. But this H+ that it's adding to the water, when we add that to the water that already had H+ and OH- in it, we've got way more H+ now. It's having a direct effect on the concentration of H+. So now that we've added H+ from the HCl, that means OH- has to go down to compensate. And that works out nicely because now it's got Cl- on this side of the table with it. So now that we've added this HCl compound into the water, we have more H+, which means we have a lower pH. The water has gotten more acidic. Please let me know. I'm not going to answer questions until the end, but if you do have a question on any of this, please put that in the questions box and I will get to it either in this webinar or in a blog post on our website. So now we look at how does this all add up to the actual water in your lagoon. What influences lagoon pH? The first fundamental aspect here is the source water that's coming in. This is your town's drinking water that then goes down the drain and becomes wastewater. What does that water look like? The biggest thing in the chemistry here is the water hard or soft? Hardness or softness in water refers to how much calcium and magnesium is in the water, because it makes it hard for soap to foam up. But where there's hard water, there's usually carbonate alkalinity. This is, we discussed earlier, calcium carbonate, limestone. If your source water in your town is groundwater and it's got limestone dissolved in it, it'll be harder water, but it'll also usually be higher pH, because when that limestone dissolves, it's giving you carbonates in the water. So that's kind of your foundation, because there's a lot more source water coming in than there is any of the other contaminants. So the pH and the chemistry of that water really matters. On the side here, we have a US Geological Survey map of hard water in the United States. The purple areas are in the US Southeast and the Pacific Northwest are the areas of softest water. And then the red are the areas of hardest water. But there's a lot of local variation. These are just in big regions. So that's something that will be specific to your water source in your town or at your plant. And then the second thing, now that it becomes wastewater, it gets all this contaminants in it. Usually those contaminants end up fairly neutral. Nobody is using so much cleaning solution in their house, dumping vinegar down the drain to make it acidic, to really offset the fact that human waste is fairly neutral. There's a lot of neutralizing effect of the source water itself. So a lot of the water times your water coming down the pipe is maybe a little bit higher than neutral, 6.8 to the mid 7s, but it's pretty close. So when all those contaminants get to your wastewater treatment plant, they start being broken down by bacteria. And this is the first lagoon specific pH influence, is that bacteria treating wastewater tend to overall produce acids. This is especially the case for anaerobic treatment. This is what you find in lagoon sludge. But in general, a lot of bacteria gain their food and their energy by ripping hydrogen atoms off of more neutral molecules. So then they're lowering the pH. They're putting more hydrogen in the water. And then lastly, we have industrial waste. And industrial waste, all bets are off. If you can name a chemical process, I guarantee you there's an industrial plant somewhere using it. So they can get a lot of different effects, whether you're operating a lagoon at an industrial plant or you're a municipal lagoon receiving industrial waste. A lot of industrial processes produce acidic or alkaline waste products. Some examples from the food industry: dairy waste is acidic, wine waste is acidic. I used to work with a plant that made tortilla chips that soaked corn kernels in hydrated lime water to soften them to create dough. So every time they dumped one of those soaking tanks, we got a huge rush of pH 11 or 12 water. So that you get a much bigger variation in the acids and bases in industrial wastewater. In addition to their normal process, they may use a wide variety of cleaning chemicals. Another example from food processing is if you're cleaning off like a greasy oil tank type surface, usually they use very basic cleaners to get those fats off. The opposite is if you're trying to clean up calcium scale or a product like that, you're going to use a very acidic product. So those can cause big pH swings. And then lastly, industrial plants sometimes mess with the chemistry of their source water. So if you've got an industrial plant in town, they're probably on the same source water as the drinking water, but they might not use it that way. They might put it through reverse osmosis or a deionized process to remove a lot of those ions. And that can actually have subtle but important effects on the chemistry of the water. One example, I'm working on a nitrification product at a plant that has deionized water because they make electronics. The other part of their waste stream is using domestic waste from their toilets and sinks at this plant. But it turns out their lagoon pH was just a little lower than you'd expect, even though they weren't doing anything particularly acidic. That was because when they deionized their source water, they're removing kind of the basic carbonate alkalinity that was coming with the water. So when that water hit the treatment plant and hit the acid producing bacterial processes, the pH dropped more than you'd expect. So the water coming out of that lagoon might only be 6 to 6.5 rather than the 7-ish you'd expect to see. So that can be a little bit more a subtle effect from industrial waste treatment. And then the last huge influence on lagoon pH is algae. Lagoons are particularly susceptible to this because they've got still water and huge surface areas and sunlight, all the things that algae likes. So algae can have a pretty powerful effect on lagoon pH. And how they do that is algae, when they're growing, when they're receiving sunlight, they consume carbon dioxide, CO2, in the water. And CO2 is a source of acidity. It keeps the pH down. So this algae just scavenges it all up, removes it from the water, which tilts the balance towards a high pH. This can have a significant effect. A lot of times, some species of algae will actually start to hurt themselves if the pH goes over 9, but other species of algae will push it up over 10 to some pretty extreme pHs. And this is the most visible, usually, pH peaks during the day, because that's when the sun is shining and the algae are most active. This effect isn't as pronounced at night, but it can be huge. And that can have serious complications for a lagoon plant. If the pH is too high, it can damage the functioning of the bacteria that are supposed to be eating BOD in the lagoon. Chlorination-based disinfection becomes really ineffective around a pH of 9. And then lastly, a lot of discharge permits just have a pH requirement that often stops at 9. So if you've got a pH above that due to algae, you can have direct violations from that. So algae is a huge driver here. So how do you control lagoon pH in this situation? The first is you have to determine the source of your problem. Is this coming in from the influent? Is it something that's coming and happening in the pond itself? And that, if you have a well-calibrated pH meter, you can determine by just testing different points in the plant. If the influent pH is normal, but then the pH in your cell is 11, you've probably got an algae problem, not an industrial plant violating their own permit and sending you horribly alkaline water. And then you need to just address the problem itself. If it's algae, it is more efficient to take care of the algae than it is to add acid to counteract its effect. Adding acid is costly and hard to control because you're trying to keep up with what are the algae doing today based on how sunny it is. It's much more efficient to try and take care of the algae problem so your lagoon is operating at a normal pH. Another way you can get bad pH is if you've got low DO conditions. If you've got organic overloading, you've got anaerobic cells. Those can start to become very acidic. So some ways to fix that is to recirculate high dissolved oxygen water from the back of the plant where the organic loading has stabled out and is not creating an anaerobic condition. If you recirculate that high DO water back to the head of the plant, it can start to fix those low DO conditions that give you a low pH. And then lastly, a solution that can help address both an algae problem and a DO problem is to add aeration and mixing. Algae really do not like to grow in moving water. So adding mixing, whether it be direct mechanical mixing or as part of an aeration system, will help stop those algae from growing to the degree that they can actually mess your pH up. And one thing I forgot to note on your last slide is that algae can mess up pH without having to look like a thick, dense, gross algae mat. There's planktonic algae that make their water still look fairly clear. You don't have that thick green scum, and they can still have a huge effect on pH. So if you've got a pH problem, you can't necessarily rule out algae, even if your pond doesn't look like it's horribly choked. So now we're moving on to alkalinity. Alkalinity is related to pH, but it's not a direct effect of pH. What alkalinity is a measure of the basic pH raising ions in the water. And specifically, alkalinity is the anti-acid capacity of the water. So you measure it by adding acid to a water sample down to a certain pH. And the more acid you need to add, the more alkalinity is in the water. So how is this related to pH but not calculatable from it? If you've got a high pH, you must have high alkalinity, right? That's not the case, because pH is just a snapshot of the balance of the water, but alkalinity is a measure of its resistance to change. So if you imagine we have two beakers of water sitting on a bench being tested. One is deionized, pretty pure water. It's got a pH of 7. The other one is a lagoon influence sample. It's murky, who only knows what's in it. It's got all kinds of stuff going on, but you measure it and it has a pH of 7. Well, alkalinity is typically measured by adding acid down to a pH of 4.5. And that can be either measured with a pH probe or by adding a colored indicator to the water. The one, I forget the name, that switches at 4.5 goes from green to red. So you add this chemical indicator to both of your jars and they both turn green because they've got a pH of 7. But now you need to titrate them. So the pure water is at a pH of 7. If you add just 1 or 2 drops of acid, boom, it's going to turn red immediately because there's nothing resisting the acid. The acid's got nothing to fight against. So even just a little tiny bit of acid is going to have a huge effect on pH because there's nothing else going on in that water. So that water has no alkalinity to it. It has no resistance to change. And then you go to your lagoon water sample that has all kinds of stuff going on in it, and you add a drop of acid, and it doesn't even notice. There's so much going on there. It's got a resistance to change that you have to add drop after drop. You have to add a stream of acid to start getting the pH to change. And that's the true measure of alkalinity, is how much does the water resist becoming acidic. So they both had started from a pH of 7, but alkalinity is a second way to kind of peer behind the curtain and see what's going on in that water. So I've mentioned a few times carbonates, which come from limestone, as an important species in pH, and they are the most important species for alkalinity. Carbonate alkalinity is usually pretty equivalent to total alkalinity in anything but the weirdest of industrial laboratory type water situations. And bicarbonate carbonic acid is a pretty fascinating molecule. It comes from 2 different places. The first one is carbon dioxide. When carbon dioxide dissolves into water, it forms carbonic acid, H2CO3. And you notice that it has two H's. So as it dissolves and becomes an acid, it does that in two phases. First one, H comes off and becomes HCO3, which is bicarbonate. And then the second H at high pHs comes off and becomes HCO3 2-, which is carbonate. So you get this relationship where it can be multiple different things at multiple different pHs. HCO3 and CO3 also come from groundwater, from limestone. Calcium carbonate is CaCO3. When that dissolves in water, it tends to pick up another H, because if you're looking here in the neutral pH range we're dealing with, this carbonic acid wants to be HCO3, that it becomes the different forms only at the extreme ends of the pH scale. So HCO3, it's coming from the air, it's coming from groundwater. This is your biggest component of alkalinity. It's going to resist changing into this other form as the water becomes more acidic. And why do we care? Why am I telling you this? And the reason we care is that carbonate alkalinity is an essential building block into the nitrification process. So if you've got bacteria that are trying to remove ammonia, they actually need that carbonate alkalinity to live. This is because nitrifying bacteria are a type of bacteria called autotrophs. They're actually similar to algae in that they gain carbon from the water, and they get their energy from somewhere else. Algae obviously get their energy from sunlight. Nitrifier bacteria get it from ammonia. But they can't do that unless there's carbonates in the water that help them build up their new baby bacteria cells. So if you don't have alkalinity in the water, you can't successfully do nitrification. You can't remove ammonia. And that is why we care a lot about alkalinity in lagoon systems. So scientists have determined that the exact ratio from nitrification is that 7.14 milligrams per liter of alkalinity are destroyed for every 1 milligram per liter of ammonia removed. But that's usually rounded up to a ratio of 8:1. If you're checking if you have enough alkalinity to do ammonia removal, you take the amount of ammonia that you have, times it by 8, and that's roughly the amount of alkalinity that you need to have available for that process to be successful. And then lastly, we need to have a residual alkalinity left over in the water once the nitrifiers are done in order for the process to work. And why is that? Why can't we just use up every last drop of alkalinity? Remember, the set point for alkalinity going to 0 is at 4.5 pH. Nitrifying bacteria die below about a 6.7 pH. So they can't get down to 1 or 2 milligrams per liter of alkalinity. You need to have 50 to 80 milligrams per liter of alkalinity left in the water to act as a pH buffer, to make sure there's enough alkalinity for those nitrifying bacteria to grow and to be happy at their pH range. So this is a figure. There's 2 major types of bacteria that perform the task of changing ammonia into nitrate. And together, they need a pH to be in the range of 6.8 to 9 to live. So obviously going down to 4.5, scavenging all the alkalinity, is not going to cut it. You need to keep that pH over 6.8. But then if you really want them to grow and perform their best, they need a pH range in a more specific range of 7.2 to 8. And that's what you can kind of see here. 7.2 is the start of this plateau. Nitrosomonas is the first bacteria. And then Nitrobacter on this side is a little bit more flexible. That pH range gives you the whole tip of this peak. So I just wanted to go into some detail about how to calculate the alkalinity that's required for nitrification. Method 1 is the simple one. You use the 8:1 rule of thumb. You take your amount of ammonia that you need to get rid of, multiply it by 8. So if you have 20 milligrams per liter that you're trying to remove, you need to have at least 160 milligrams per liter of alkalinity in the water. This can be done as a check. A lot of times you're going to calculate 160 and then you look at your water test and it's showing 250 milligrams per liter of alkalinity and you say, good, we're good to go. Method 2 is more specific. This is when you're actually trying to calculate the alkalinity that will be left over after the nitrification process is done. And this is more important when A, you're going to have to supplement alkalinity, you don't think you have enough, and you're trying to calculate how much alkalinity addition you need to add. And B, if your alkalinity from this check number 1 is pretty close to the limit, you don't have a lot to spare, this calculation will help you determine, do you really have enough? How much margin of error do you have if you've got a tight permit and if actually, oops, you're 10 milligrams off on your alkalinity and that gives you an extra milligram per liter of ammonia in your effluent, is that going to mess up your compliance with your permit? So in this one, you take the exact 7.14 that the scientists have provided us, multiply that by your ammonia that you're trying to remove, and then you add your margin of error, your residual alkalinity, which can be 50 to 100 milligrams per liter. So in this case, we take our 20 times 7.14 is 142.8, add 50, and that gives us 192.8 milligrams per liter of alkalinity required. Again, we're removing the same 20 milligrams per liter of ammonia, but this calculation gives us a higher number. This has a higher factor of safety and a little bit more detail. So if you're trying to do detailed calculations, if you're close to the wire, or you're trying to estimate how much alkalinity addition you need to add, this is the calculation method 2 is what you want for greater accuracy. So now we move into our final phase here, which is directly controlling lagoon pH by adding alkalinity supplements. You can use these to control either alkalinity itself or pH or both. Each of these substances will affect those in different ways. They've got a kind of a more powerful or less powerful effect on the pH and total alkalinity. But this is just an overview of 4 of the most common alkalinity sources for wastewater treatment. The first one is lime, also known as hydrated lime or slaked lime. That's usually sold as a powder. The second one is soda ash. If you're curious about baking soda functions fairly similarly to soda ash. Also usually sold as a powder. Usually it's fairly inexpensive because it's an industrial byproduct in a lot of cases. The third one is caustic soda, sodium hydroxide. I refer to this a lot in industry just as caustic, usually sold as a liquid. And then lastly, we have magnesium hydroxide. That's actually milk of magnesia, same as in pepto-bismol. Can be used in wastewater treatment. And of these 4 chemicals and the ones related to them, each of them have some pros and cons. So I'll just go through those briefly. So lime, the major pro is that it's the cheapest of these options. It's widely available. Everyone has it. It's easy to store as a powder. The equipment you need to handle it is some kind of solids handling, like a hopper or bag storage, or whatever quantities you get, those have to be stored, and then that powder has to be slaked with water and turned into a slurry so it can be pumped into your water, into your lagoon itself, into your process. So the pro there is inexpensive. The cons with it, you need a little bit more upfront equipment cost because you're trying to have the solids handling, slurry forming equipment. And then lime has some drawbacks because it's bulky. It has all that calcium in it, that it can cause calcium scaling of the feed lines, of equipment. And then it also really bulks up your sludge. It just adds mass, which in a lagoon plant can be pretty killer because you're paying to add this lime, which contributes to the sludge blanket, which then you're going to have to pay to dredge sooner than you otherwise would have. The scaling issue is not insignificant. I once worked with a landfill that was having an ammonia problem, and they turned their lime dosing system up as high as it would go, and they actually scaled one of their main influent pipes shut between two of their reactors, and they had to emergency take the plant offline to clean all the lime out of the pipes. That's less of an issue in a lagoon where you're feeding into a wide basin, but it does have its drawbacks. Soda ash has a lot of the same benefits as lime in that it's sold as a powder. It's relatively inexpensive, but it's a little bit easier to dilute, to make a slurry out of. It doesn't have that scaling issue from the calcium, and it's a little bit easier to handle than lime. But some of the drawbacks here is this is the weakest alkalinity source of the bunch. You need more of it to get the same effect. And then as you're adding all of that, it does have these 2 sodiums in every molecule, which means you're putting a lot of sodium in your effluent, which can have effects on TDS limits or just overall salt permit issues. Caustic soda is a very popular option because it is easy. You're getting caustic soda in as a liquid. A lot of times plants will just have a bulk tank on site. The chemical company backs up a truck, fills up the tank. You don't actually have to handle or transport any powders. You don't have to make dilutions. Goes from the tank, gets pumped into the process, and you're done with it. Advantages to caustic soda here is it's very powerful. You get a lot of pH effect from it, and it's easy. There's no solids handling required. The drawbacks are it is more costly than the powdered versions, and it's very, very hazardous. This will do nasty things if it gets on you, so you need a lot of PPE to handle it safely. And then also caustic soda in its most concentrated form, a 50% solution, it freezes well above the freezing point of water. It'll be a solid by 50 degrees Fahrenheit and starts to get really thick couple degrees above that. So if you're a lagoon plant, you don't have a building that's heated, you're going to have some kind of insulation and heating solution for your tank in cold weather so that your caustic soda does not freeze. And lastly, we have magnesium hydroxide. Magnesium hydroxide has a lot of the same advantages as caustic soda. It's sold more as a slurry, so its tank does need to be agitated. But that's not a huge deal. It's still usually delivered as a liquid and dosed as a liquid. But it has some significant upsides. Unlike caustic, magnesium hydroxide is not nearly as hazardous to operators. It's got a lower pH, and it actually makes it harder to overshoot pH in the lagoon. If you add too much caustic to a lagoon or to a body of water, you can easily end up going way past the pH that you wanted, versus magnesium hydroxide will start to slow down, and it's hard to overshoot a pH of 9 using magnesium hydroxide. Downsides to it, it is still a specialty product, so you can only get it from certain suppliers, and it is about equivalent in many cases to caustic, but it's on the more expensive end. So those are the main 4 alkalinity adjustment chemicals. You have other ones like baking soda, that sodium bicarbonate, that might be more available near you. Chemical representatives will be able to give you pricing and bench testing to determine what might work for you. But how do we dose these? There's 2 major methods to how you dose these. The specific equipment you use, there's a much wider range, but generally the overall dosing philosophy falls into 2 categories. The first one is bulk supplementing. This, you're just adding some alkalinity or pH adjustment to a lagoon basin. This can be continuously. We're adding it every day on a continuous basis, or you only dose as needed. One plant I've heard of does this when their ammonia limit drops to the summer level, is a lower level than their winter level, and they need to get over that drop. They need to kind of supercharge nitrification in their lagoon for a little while. They add soda ash to their pond to raise the pH up into the really effective range, and they help those nitrifiers speed up in the spring when they're still a little sluggish, to help them meet their lower summer ammonia limit. And this is generally the lower tech option. You make some kind of slurry or you have some kind of tank. The tank that's shown in the picture here was a soda ash slurry tank that the operators mixed that up. It's covered so it doesn't get rainwater in it. And then it gravity drains into the plant at an adjustable feed rate and just drains into the cell to provide alkalinity to help them get their ammonia down in the lagoon. This is generally going to be manually adjusted. If the pH is a little high today, you add a little bit less tomorrow. So this is just bulk supplementing, low tech, just help the plant nudge it in the direction that it needs to go. The opposite viewpoint from that is very specific pH-based dosing. This is where you've got a pH probe in the water, and then you've got a controller that turns your dosing pump up or down based on the pH to hit a certain set point. This is most effective if it's done in a small, highly mixed chamber, where the pH probe can get a much more accurate reading on the pH versus trying to get an accurate average reading out of a lagoon cell. So this is something that we're going to be doing at my electronics plant with the nitrification reactor. We're actually going to build a small influent chamber onto our nitrox reactor, which is where the pH control will be done. To save costs, they're only going to add as much supplemental chemical as they have to at a certain pH set point that we're planning to be about 7 to 7.2. We'll turn that up if we need to. So water will be pumped in from the lagoon to this small chamber that's being mixed by the force of that water. The pH probe will be in there, and a pump will turn on or off or turn up or down to maintain a set point. This is great if you're trying to minimize cost, if you do need a lot and you're not trying to overshoot, or if you've got any other process that's pH-based. You can get pH-based process to drop out heavy metals if you've got those in the water, or if you need a certain pH for your coagulants to work, if you're trying to remove phosphorus later down the line. pH-based control is the precision approach versus the bulk supplementation approach. And that is it for our water chemistry webinar today. Went over pH, went over alkalinity and how algae and nitrification both contribute to that and depend on that. And do we have any questions? I'm opening up the questions tab now. We've got a question. Can you have a pH outside of 0 to 14? No, you cannot. That's just as high and as low as it goes. And it's actually extremely difficult to get the two sub 1 up to above 13, 14, just because you're at the extreme edge of an off balance water system. So that's when you get your very extreme acids and bases. We've got a question on the average level and range of alkalinity. In the places I have lived in my life, including Illinois and central Pennsylvania, alkalinity was often between 150 and 300 milligrams per liter. But also in my travels, there are places where it's under 50. There are places out west with high alkalinity that it can be over 400 milligrams per liter. So the range is pretty huge, just depending on where you are. If you're looking at a water report, also, I'm talking about alkalinity and water hardness in milligrams per liter. Sometimes that's reported as grains per gallon. 1 grain per gallon is 17.1 milligrams per liter, if you need to help translate that. We got a question. Yes, nitrifiers use up alkalinity. They destroy the alkalinity in the water. And one thing that I had meant to write down and didn't is that actually if you go through a denitrification process after nitrification, it actually puts the alkalinity into the water, back into the water. It undoes that alkalinity destroying effect. Do colder water temperatures affect alkalinity in uncovered lagoons? Not directly that I know of. They'll have a little bit of an effect if you've got less algae growing. That can mess with pH. But generally, the alkalinity is set by your source water, and that does not change hugely throughout the year based on temperature. If you're seeing nitrification effects, that's probably just because the bacteria are slowing down. Question, can we have a neutral pH and low alkalinity? Absolutely. That can just mean that you don't have a lot of acid in your water. You don't have a lot of alkalinity, you just have a little bit of a tighter balance versus a lot of acid and a lot of alkalinity. You just have less of both, and that can still add up to a neutral pH. Alrighty, I think that's all the questions that I've got. We'll put a write-up of all the questions on our blog probably next week. So if you have a question that I missed or didn't get to, please check back there. If you have any feedback on additional questions that you have, please let us know in the survey after the webinar. So thank you guys very much for joining us.